Hello, today I'm going to talk to you about orbital diagrams and electron configurations. So we have already talked about how there are different energy levels within the atom, and that whole number in the front with the lines we looked at in the previous lesson, that is our principal quantum number, or the energy level as a whole. All right, so today we're going to talk about breaking that down even more. So in the very first energy level, we just have a very simple configuration, and then as we move up, it gets more and more complicated for each level. All right, so an orbital diagram is going to allow us to show where the electrons are located within each of those levels, and then the electron configuration is kind of a code that tells us what's going on in the atom with where the electrons are. All right, so each level, like we talked about yesterday, is broken up into sublevels, and then within each sublevel we have orbitals. So in the very first level, we only have one sublevel, and it only has one orbital, which is S. As we move to the second one, we have S and we have P sublevels, and then the P sublevel has 3 orbitals, right? And then as we move up to the third level, we have S, and then we have P, and we have D, and D has 5. So it gets more and more complicated as you move further up into new energy levels, and there's more space for more and more electrons as you move up. Okay, so an orbital, just for definitions, is a space where we can put 2 electrons, all right, and a sublevel is like it sounds, a level within the major energy level where there are orbitals that have the same energy. Okay, so a sublevel could have 1 orbital, or 3, or 5, or 7. All right, so now let's get into how we actually draw the orbital diagrams that I just showed you on the first slide. So we always start at the bottom, all right? That's where our lowest potential energy is, right? That's where our electrons are closest to the nucleus, and then we move up. This big number in front tells us which principal energy level we're in, and then the letter tells us which sublevel it is, and then each box represents an orbital, all right? And then within those boxes, we put arrows, all right? We can fit up to 2 electrons in an orbital, and we represent that by 2 arrows, all right? And they have to have different spins. This is because of the rules of quantum mechanics, which is kind of outside the scope of this course, but know that when you put electrons in an orbital, they have to have opposite spins, which we represent by opposite directions of the arrow, okay? The up and the down are arbitrary, they just mean they're opposite. Okay, so we always start in the bottom level, and we'll fill that before we move up to the second level, right? In the example I have here in your notes, we're drawing the orbital diagram for sulfur. So if we look at our periodic table, sulfur has 16 electrons, right? It has 16 protons, so it'll have 16 electrons in a neutral atom. So that's how many arrows we need total in our diagram. So we've got 2 already, right? Next we'll move to the 2s, all right? That's the next lowest potential energy, so that's 4. All right, when we get to the P sublevels, right, we are going to put 1 in each orbital before we double up and add 2 in any. And the reason for that is electrons are negative charges, remember? So if possible, we'd like to spread them out because they're going to have some amount of repulsion. So we don't double up until all of the spaces are full. So we've done 3, and then we'll go back and double up. Okay, so now we have 10 electrons, 2, 4, 6, 8, 10, right? So we need 6 more. So we'll fill 3s, because that's our next level up. And then for 3p, we'll put 1 in each, all right? And that only gets us to 15, so we'll come back and double up with 1. And when we put 1 in each, they should all have the same spin, or all be facing the same direction. Could be up or could be down, but they have to be the same, right? So then our last one goes in doubled up in one of those orbitals. Okay, so this is our ground state ground state orbital diagram for sulfur, which means it's the lowest energy conformation we can make. Okay, I've only shown the first 3 levels here, and so far we're just going up a level and up a new sublevel, right? P is a little bit higher energy than S, and so we fill it after S. Once we get to the 4th level, it gets a little bit more complicated. oh, sorry, let's do the configuration first. So the configuration is just a summary of what we did. So in the 1s orbital, that's the 1s here, we have 2 electrons. In the 2s sublevel, we have 2 electrons. In the 2p, we have 6, so there's 6 here. The 3s has 2, and then the 3p has 4. So that's where all our numbers come from. All right, and you can always add up these superscripts and make sure you get the number of electrons that you should have for the atom. All right, now, if we were to continue going, if we put the 4s in here, you can see it's pretty close in energy to the 3d, all right? And you'd see that on that first slide too, and the diagram in your notes. So once we get here, we don't actually continue to fill 3d, we fill 4s first, okay? For ones where you actually have to fill it in like this, I will not go beyond 3p, all right? The others we would do with the periodic table, and I'll show you in a minute why that makes sense. Let's do one more definition. So we have now shown the entire orbital diagram and the entire electron configuration. You can imagine that that gets tedious as you get more and more electrons. And so we have an abbreviated way to express the electron configuration. Basically what we're going to do is say, okay, everything in the first and second level is full. So I really only care about what's happening in this top level. Right? That's where things are most likely to move around. So we're going to summarize the electron configuration by condensing this whole filled lower levels with the noble gas that corresponds to. Right? So on the right side of your periodic table, the noble gases are this last column here, which you should know. Okay. They are all completely full in their outer energy shell, okay? So when we do these configurations, we should always have the number of electrons that is one of these when we do our filled shells. So here we have 2, 4, 6, 8, 10 electrons in our 1 and 2 energy levels, right? So 10 electrons is neon. Okay, and if we were to draw the electron configuration for neon or draw the orbital diagram, it would look like what I have in the red box here. Okay, so now this is the same as this, and we're just going to write that as neon in brackets like that, just the symbol, and then summarize everything that's outside of the box, so the 3s2 and the 3p4. That's the way we do our abbreviated configurations. All right, let's do one more example with an abbreviated configuration. This time we're going to do nitrogen. All right, so first we've got to find nitrogen on our periodic table. It is over here. It is number 7, so it will have 7 electrons, right? So we start at the bottom again, 2 in here, 2 in here. All right, we're at 4. Now we have 3 more left to put in. We're going to put 1 in each p before we start to double up. All right, and now we've gotten to 7. So that is our total number of electrons for this element, for nitrogen. And so if we write our electron configuration, it'll be 1s has 2 electrons, the 2s has 2, and the 2p has 3. Okay, if we do the abbreviated form, the only level that is full, all right, is the 1s. Okay, that is 2 electrons, and it corresponds to helium, which is our very first noble gas. Okay, so we'll use helium in brackets and then summarize everything else that's in the outermost energy level, or the highest potential energy level that has electrons in it. All right. So now we can simplify the process of finding these configurations if we use the periodic table. All right. So our periodic table, I mentioned before, is organized based on the number of electrons that we have. So if you notice the first 2 columns, there's just 2, right? And that is called our S block. It's because everything in that column, the outermost electrons, like the highest energy electrons, the last ones we'll put in, are always going to be in an S orbital. And the S orbital only holds 2 electrons. Okay? This section over here is called the P block. All right? All of those elements will have electrons in their in a p orbital in their highest energy level. The D block is here. All of those will have electrons in the D, and then the F is down here, which we aren't going to use a whole lot. Those are unstable elements. We use them in nuclear chemistry, but not very much beyond that. Okay, so if we find our element on the periodic table, so we're doing chlorine, it is located right here. Okay, so we should know, looking at this, that the last electrons we'll put into chlorine will be in the 3p sublevel. Okay, so we can start at the top, always starting with 1s, and fill in the electron configuration just using the periodic table. So we'd have 2 in the 1s, 1, 2 in the 2s, 1, 2, 3, 4, 5, 6 in the 2p, 1, 2 in the 3s, and then 1, 2, 3, 4, 5 in the 3p. Okay, so our electron configuration would look like this. All right, and so you don't have to remember how many things go in each sublevel. It's all laid out for you here on the periodic table. Okay, so let's do one more example. This time we'll do the abbreviated configuration. So let's find selenium. It is number 34 on the periodic table. It's located right here. Okay, remember for our abbreviated configuration, we only care about the outer or the highest potential energy level. Okay, so that's only this last row in the periodic table. So let's locate the noble gas that's just before it, right? So there's a noble gas here that's closer, but selenium doesn't have that many electrons, so we have to go to the one before that. Okay, so this noble gas is argon. Okay, so we'll write that in the brackets. Okay, and now the rest of it we can just write starting with this last row here. So the next after argon would come 4s, and we'd have 2 electrons there. Then 3d, because remember I said 4s and 3d are very close in energy. Okay, but the periodic table tells us which level we should go to next. Okay, and then last but not least, in our 4p we have 1, 2, 3, 4 electrons. And so that's how we would finish our electron configuration. Okay, we're going to do some practice with this and play some games to hopefully make it clearer. But that is the gist of writing electron configurations.